early on.
Good morning. Morning, Dr. Stephen Ashworth. I'd like to welcome you from the UEA to talk to everyone today about light-powered therapeutics. So welcome.
Oh, it's over to me, is it? That
it's
was
over
quick.
to you.
Okay, good morning, everyone. It's lovely to be here. And I've been invited to talk to you today about light-powered therapeutics. So what I need to do is share my screen, which I will try to do like this. And we can get on with it.
I'm just going to turn my camera off so I don't distract anyone.
And so I hope you can all see that.
Yes, we can see it.
Wonderful. Okay, so we all know the title of the slide. My name is Stephen Ashworth. You spell Stephen with a PH because I'm a chemist. And I'm actually from the area. I went to school in Norwich, born and brought up in this area, and then went off to different places for study at university. And then once I'd done my doctoral degree, so once I'd become a doctor, I did some work in the United States and in Germany as what's called a postdoc. And now I work at the School of Chemistry at UEA. I'm mainly involved with physical chemistry, but that has also got me involved with the physics program, which is new there. And I'm actually, at the moment, I'm head of physics program, but which is based in the School of Chemistry. My main task outside the School of Chemistry is to do things like this, in fact, to be a science communicator. Here are a couple of pictures of me doing my what's called my kitchen chemistry show. That's actually somewhere else in the world, and I've missed the travel this last year or so. But what we're going to talk about today is light, because that's one of my major research themes has been light. I've either been using lasers to look at molecules or building lasers to use to look at molecules throughout my career. So this is what we're going to cover today. I want to go back over the use of light in therapeutics. And then I want to talk about these things called sensitizers, which are a key component of using light in therapeutics. And then I want to talk about the things that I've actually done research on myself, which are a class of molecules called phthalocyanines. And the phthalocyanines have some of the properties that we need for a good sensitizer. And then to finish up with a bit of the talk at the end, is going to talk about the photophysics of these things. So this is essentially my research, where we've taken a molecule and tried to work out how good it's going to be at taking that light and putting it places that are good for therapeutics. So the first thing is to get clear what we mean by therapeutics. And the word therapy is the attempted remediation of a health problem. So these are just some definitions that one can find across the web. And so we get the therapy from various roots, meaning curing or healing. And so that's what we're looking. Therapeutics are things that we can use to cure or heal. And light therapies have been known for a surprisingly long while. So in Egyptian and pre-Hindu times, there are records of certain plants that contain molecules called psoralins, and these were applied to areas of the skin that were lighter than others. So this is a condition known as vitiligo. And it's where the skin in patches doesn't create the melanin that would normally give you the color of the skin. Now, there are a few famous cases of this. Perhaps you know the model Winnie Harlow. She's a famous model with dark skin. And of course, when there's a patch of skin that doesn't create the melanin that gives the skin that darkness, it's very obvious. In a light-skinned person like myself, I have small regions of vitiligo. It seems to be hereditary, and it's not so obvious as it is when there's a larger contrast. And what the Egyptians pre-Hindus used to do was apply these psorolens to the areas of the skin that were affected, and then they'd be exposed to sunlight. So that's where the light therapy comes in. And that was found to help and darken the skin in those areas. Lupus vulgaris is a disease or a condition where there are nodules under the skin, and these can be treated with the bright light from a carbon arc lamp. Now, a carbon arc lamp is a lamp that simply has 2 carbon electrodes, and you put a very, very high current across those 2 electrodes, and it produces a very bright light. So obviously these were lamps in the very early days of electricity. And Niels Finsen, who developed this technique, won a Nobel Prize for it. Another very well-known example is the case of neonatal jaundice. This was accidentally, the light treatment from this was accidentally discovered in 1956. What happened there was a sample of bilirubin, which is the cause of yellow baby syndrome, which is this is what we're talking about here. Baby is born and it's extremely yellow, and that's because bilirubin, this pigment, is not being broken down properly to something that can be washed out in the bloodstream. So basically you have something that will dissolve in fats and oils, but not in water. But if you can turn it to the lumirubin, which is an isomer, it's just a change in the structure, it becomes soluble in water, and then it can be removed from the body. And there was a sample of this bilirubin was sitting on a sunlit windowsill, and they found that it had become water soluble just by exposure to sunlight. And so this is now a standard treatment for neonatal jaundice. You expose the babies to the right wavelengths of light. The bilirubin, which is dissolved in their fat, then turns into lumirubin, and it can get washed out in the body through the bloodstream because it dissolves in the blood. So these are some light therapies, and you can see they're starting to become more specific. We're starting to know a bit more about what is actually going on in these therapies. Now, scientists love to classify things. We're inveterate classifiers, and the point is you like to put things in boxes. And so you can say, oh, this belongs in box A, or this belongs in class 2. And so there are different classes that we can give to light therapy. So you have a direct phototherapy. So photo is saying that the therapy is to do with light. So you have direct phototherapy where the light interacts directly with your target. And that is something like, probably like, almost like the Egyptians, or the carbon arc lamp we've just seen. The light is interacting directly with the thing that you're trying to treat. If you have something like psoriasis, so this is a skin condition, and there's a drug there that you can put on in a cream and then expose it to the right wavelengths of light, and that turns the ingredient in the cream into an active ingredient. So what you've done there is, I think these things are called prodrugs. So they're not drugs when they're applied or when they're taken, but you do something to them, the body might do something to them, or in this case, light does something to them to turn them into an active compound. And so you have psoriasis, you put on this inactive compound and expose it to the right wavelengths of light, and that turns it into an active compound, which then goes on to treat the condition. And then we have what's called photodynamic therapy. So this is a form of indirect phototherapy where the light interacts with a third party. What I mean by this is you put something into the body. In this case, it's the body because we're trying to cure something in humans. We're putting something into the body that will absorb light. And that third party, it's what we call a sensitizer, that then can transfer the energy somewhere else. And once it's somewhere else, it can then do its job. That's a bit abstract. Let me go through it with what we're going to do here. What we have is this blue dye. That's an example of a phthalocyanine. So that lump of pigment you can see on the screen is an example of a phthalocyanine here. That is what's taken into the body. You shine a light at it. The phthalocyanine, you can see it's highly colored. So what it's doing is absorbing a lot of light very easily. The energy in that light is then transferred, in this case, to oxygen. And it's the oxygen that then does the therapy for us. Now, to understand how this is going to happen, we need to understand that the oxygen we breathe is given this designation. So this, to someone who knows about these things, this gives you an awful lot of information. The key thing for us is this 3 here. This says that it's a triplet state, okay? This 1 tells us it's a singlet state. So the 1 tells us it's a singlet, the 3 tells us it's a triplet. Now the triplet, this is the ground state. This is how we find oxygen in the air around us. This is how we find oxygen dissolved in the fluids in our body. Singlet delta oxygen, on the other hand, is not the ground state. It's got energy in it. It's got excess energy, and it can do something with that energy to get back to the ground state here. So this is the lowest energy state, and we can put energy in. We can make this state. Unfortunately, we can't go from here to here by simply absorbing light. That's a very, very, very inefficient process. So we have to go around the houses, and that's why we need the sensitizers to get energy into here. Once we've got energy here, that's a very destructive form of oxygen that will kill cells. And if we're dealing with cells that we don't want in the body, such as cancer cells, we can see that that might be a good thing to be able to produce, and a good thing to be able to produce in a localized area, so just close to the cells we want to kill. Now, if we're going to do this, if we're going to get energy into the oxygen, as I said, we need to go around the houses, and that's why we need the sensitizer. The sensitizer is going to be something that absorbs lots of light and then transfers the energy to oxygen that's in the environment. Ooh. So what do we want from our sensitizer? If you were an engineer and you were told to go away and design the perfect sensitizer, what would be the properties you need for that sensitizer? Well, the first thing we need to do is absorb lots of light. So the term we use for this is a high absorption coefficient. That means that it's going to absorb lots of light and absorb light easily. And ideally, we want that to be not just anywhere, but to be in the region 600 to 850 nanometers. Now, this is a light of relatively long wavelength when we're talking about visible light. 600 nanometers you can see, 850 nanometers you can't see anymore because it's too long wavelength, it's too red for you to be able to see that anymore. And why we want absorption in this region is because that's the region that penetrates skin, skin and cells very well. So if you've got a mass of cells that you want to kill, it might be a cancer, a lump of cancerous tissue, you're going to want your light to get as deep into that as possible. Now, we can get light just about anywhere in the body with a fiber optic, but we want to get it into those cells, that mass of cells. And so that's why we want to use these wavelengths, because that's going to be good at penetrating living tissue. We want a compound that we can give to a patient and that's not going to kill them, whether or not the light is shining on them. So it's got to be a harmless compound, something that you can give to a patient and it's not going to cause any side effects when the light is not on. So we don't want these things to be toxic in general. We want the singlet oxygen quantum yield to be high. Now, what this is saying is that we, for each photon that we absorb, we want as many as possible singlet oxygens produced. Now, the maximum singlet oxygen quantum yield is 1. That means for every 100 photons you absorb, you produce 100 of these energetic oxygen molecules. Now, generally, we can't get to 100% or a quantum yield of 1. So what we need to do is get that as high as possible. And when in these sorts of things, if you're over 60%, that's good. So we're looking at something that for 100 photons absorbed will give us at least 60 energetic oxygen molecules, these singlet oxygen molecules. Now, it turns out that lots of molecules that absorb in the region 600 to 850 nanometers have properties which make them stick together very easily. Now, we don't want them to stick together because that's going to change the way they interact with light and how they give it to the energetic oxygen or give it to oxygen to make it energetic. So we need to have as little as possible of this sticking together, the aggregation. Ideally, we want the sensitizer to be retained in the target tissue and not elsewhere in the body. So the worst thing you want is to find that you have taken a drug that's going to kill cells in your body. You walk out into the sunlight and you find that you are having a reaction to the sunlight simply because the light is interacting with your with this drug. And in fact, in the early days of these sorts of therapies, that was the case. Patients would take a drug and then have to be isolated in dim and dark conditions for up to a week or two before all the drug was flushed out of the body. So you'd like to get this drug into the target tissue and not everywhere in the body. And there are also other features you want. Ideally, you'd like this sensitized to be robust. You don't want it to break down if it's sitting in a bottle on the shelf. You'd like it to be a single substance. It's much easier to work with single substances than a mixture of substances. When the body starts to break it down, you want those breakdown products, the metabolites, to be non-toxic. You don't want them to poison the patient. If you're having to synthesize this, you need to be able to make it easy, an easy route to synthesis, and make it reproducible. And you want to get rid of the thing from the body. So you want it easy to elute, a technical term for washing it out of the body. So now we come to the class of molecules that I have actually done some research on. And these are the phthalocyanines. Now they have some similarities to heme, so hemoglobin. And this is the particular family that I was looking at. So what we see here is this molecule. Now, all these double bonds alternating with single bonds all over here. There are two things that this does. A, it means that it will absorb light easily and of these long wavelengths because there are so many of them. And secondly, it means that molecule is flat. And that means that these flat molecules, because of the way the electrons are in the molecules, they love just to stack up like chips you see in a casino, just stacking up like that. These groups in the molecules I was looking at, these are all the same, and they're all at these positions. So there might be a chain here with 15 carbon atoms on, or 2 carbon atoms on there. So these can be different, but in one molecule, they're all going to be the same. So if this one is just a methyl group, CH3, then it's a methyl group here and here and here and here and here. They're all the same. Now, of course, there are other phthalocyanines that one can imagine with these R groups. Instead of being here, they're here. And these molecules have some advantages for sensitizers. They are very easy. They absorb light very easily, and it's in the required region. They're very stable. In fact, if you have recently seen a CD that looks blue on the bottom, so these are often sold as rewritable CDs for computer systems. I know we're moving away from that. CDs tend to be old technology now, but if you take a look at CDs, there are generally two types, and one of them is this blue, has this blue coating on it. It is one of these sorts of molecules because they are so stable. They're also non-toxic, so you can take these without harmful effects. They will localize in tumors, so a tumor will absorb this selectively, and they have a high singlet oxygen quantum yield. So when you put light in, these will effectively produce this energetic form of oxygen. And a couple of rather large disadvantages. They, as I said before, they stack together very easily. So that's what I mean by facile aggregation. They just love to stack up, and they are not very soluble in water, which is a bit of a blow if you're trying to use a system of water channels, which is essentially what our bloodstream is, to get the molecules where you want them to be. One other thing that I haven't mentioned about this yet is the metal sitting in the middle. So this is another change we can make. We can make different metals here, and we can also have no metal here. If there's no metal here, then 2 of these nitrogen atoms will have hydrogens on them. So there's, again, that's another change we can make. Not only can we change these R groups and the position of those, and the nature of those, we can change the metal in the middle. So it might be zinc, might be a palladium, it might be a non-metal even. We can put silicon in the middle here as well. So there's a whole family of different molecules that we can consider for these applications. So now, if you've got a molecule like this, and what you need to do is have a look at what's called photophysics. So what we need to do is evaluate how much light they will absorb. So that's the absorption coefficient. We need to evaluate how efficient they are at producing this energetic singlet oxygen, which is the quantum yield. And one of the steps on the way to doing that is to evaluate how quickly you form the triplet state of the phthalocyanine. And I'll explain why that's important in a moment. And then we can look at how quickly your excited absorbers. Now, the excited absorbers are those things that are in your system that have got energy in them. So the first thing we do is put energy into the phthalocyanine. That energy then has to get to the right place to enable the phthalocyanine to efficiently excite or give that energy to the oxygen molecules. And so if you've got energy in your system, how quickly that gets dissipated, how quickly that turns into heat is also something that you want to know. So that's the relaxation rate of our excited absorbers. That's how quickly the energy that we've put in to, say, our phthalocyanine gets turned into heat. So the first thing is relatively straightforward. We look at absorption spectra. So we take a sample of our molecule, we dissolve it in an appropriate solvent. In this case, the solvent would be toluene, and the toluene you put, or methylbenzene, and you put a dash of pyridine in that to stop them sticking together, to stop these molecules sticking together. And what you see is that as you change the wavelength across here, so this is basically the visible region, we start, we start at the this end, which is just into the ultraviolet, and we go out to this end, which is in the infrared. So you can't, some people might be able to see in this region, but not everyone. Some people might be able to see in this region, but not everyone. But all this area in the middle is generally regarded as the visible. So we have some ultraviolet absorption here, and we can see the very strong absorption for these two different molecules are here and here. So this one is the bare phthalocyanine. So this is the phthalocyanine without a metal in the middle. And this is the phthalocyanine with a metal in the middle. So you can see that's shifted the absorption just slightly. And so as we go along from left to right, we can see in different regions. So here in 500 nanometers, so that's basically green. We're absorbing nothing. We get to the red, we get this very, very strong absorption, which is what we want in this region that's good at penetrating skin. Another way of looking at this is to look at what is given off in fluorescence. So there we put in some energy and we look at the wavelengths that are given off. And so we can compare this with the absorption spectrum. Here we have this black line, this the absorption spectrum. And we have an excitation spectrum. So that is where we're looking out here at a wavelength. And as we put this wavelength in, we measure how much of this wavelength comes out. So we change the wavelength we're putting in. So that's this line. We change the wavelength we're putting in. And we see how much of one wavelength comes out. In the emission case, we put in one wavelength, which is probably up here somewhere in this region, put in a wavelength there, and we look at the fluorescence, the wavelengths that are given out by that molecule. Now, what I've done here is I've made them all the same height so that we can see easily, we can compare easily what's going on. They're not all going to be the same height, so don't be fooled by that. And this wavelength is going to be key for us because we're going to be using this in our experiments later. So remember that at 355 nanometers, all these molecules do have this absorption. So we can put energy into the molecule here, and we can see then how it moves through the molecule and how that energy gets out into our oxygen. And that's what we're going to be looking at. So this is a diagram which is going to look complicated by the time I've finished with it, but it's a way of simplifying what's happening to all the energy that we're dealing with in our molecule. So we have some states here. This is our phthalocyanine in this gray box, and these are the energy levels that we're going to be dealing with. So these represent energy levels, and if we put, if this absorbs a photon, we take a molecule which is in this lowest energy state, and we put some energy in. Now we can only put energy in that will take it to another energy level. That's what quantum mechanics tells us. And so we might put it up here somewhere. And why we call this S0, it's because it's a singlet state, and that 0 just tells us it's the bottom. S1 is the next one up. So there's 1, and then there's going to be 2 and 3 and 4 as you go further and further up. And S stands for singlet. So these are singlet states, and these are the normal states that you will deal with when you're dealing with molecules and absorbing things. But when we do get energy up here, this molecule doesn't like that. It prefers to be in this bottom level, just like this one likes to be in the bottom level, right at the bottom. Once you put energy in, this wants to get to this bottom level. And it does it very, very quickly, extremely quickly. And that's what we call, that process is called internal conversion. So we're converting energy, and we are, no, sorry, back up there. So it likes to get down to this level. Now, when it's got to this level, it can undergo a process called internal conversion. And that means it ends up at a high energy level of this, because these energy levels, they don't finish where I've drawn the last black line here. They keep going up and up and up and up. That's what this gray box is meant to represent. These just keep going on up and up and up. And so this can escape from this high energy level by transferring onto this set of lower energy levels, and then it can rattle down and find its way back, because ultimately these molecules need to get back to this bottom level. It's like rolling down a hill. You've pushed it uphill, and all it's trying to get down to the bottom of the hill every time. So that's one way it can do it, with this internal conversion. Another way it can do it is just to spit out a photon. We've put a photon in, we've put light in, and we're getting light out. That's called fluorescence. So here, this way, we don't get any light out. It's called a non-radiative transition because it's not producing radiation, it's not producing light. Here, we've got a radiative transition. It's producing light, and this is fluorescence. And this happens quickly. Now, to give you an idea, this happens on the nanosecond time scale. So we're talking 10, 20 nanoseconds maybe. This happens on a picosecond timescale, which pico to femtosecond timescale, which is 1,000 to 1,000,000 times quicker than the fluorescence. And we can measure these timescales. So we know that this goes up here essentially instantaneously. This happens very quickly, so picoseconds to femtoseconds, and this happens somewhat slower, nanoseconds. Well, nanoseconds, you might know nanoseconds is times 10 to the minus 9 of a second. And this is 1,000 to 1,000,000 times quicker. Now, the other thing we could do, as well as doing this internal conversion, is called inter-system crossing. Now, inter-system, because you're going from this set of singlet states to this set of triplet states. Now, you notice we don't have a T1 because T0, we don't have a T0 down here because T1 is the lowest energy we can get in the triplet states. And these are what we need to produce to be able to give energy to our oxygen molecules. So we've got inter-system crossing here. We're changing a singlet to a triplet. And we can have an absorption from the triplet state. And we'll see an example of that a bit later. So we get this energy pumped into our molecule, and it can go all these different ways. And then finally, we can get this transition from our triplet state. And so as you notice, if that happens, this absorption fades away. Let's try that again. As this happens, this absorption is fading away. What's happening there is we're emptying this level, slowly draining away down to here. And that's a process called phosphorescence. And that takes place on a very long time scale. Remember, we said here we were picoseconds and femtoseconds. Here we've got nanoseconds, which is 10 to the minus 9. This is really long. This is microseconds. So this takes place on a time scale of maybe 20 to 300 microseconds, which is really long on these time scales. And that phosphorescence is something that we can detect. It's very, very weak, and it's very, very long wavelength, which makes it very, very difficult to detect, but it can be detected. Now, if we have gone up here and we managed to produce these, the molecules in this state can end up here, rather than spitting out a photon, rather than doing that phosphorescence, it can transfer the energy, a bit like handing the baton in a relay race. It can transfer the energy to an oxygen molecule, and that energy gap is just enough to get this oxygen molecule to be the energetic cell-killing singlet delta oxygen that we want. And then if there are no cells around to kill, the only thing that this one can do is spit out some phosphorescence. And again, that's phosphorescence because it's slow, it's weak. And the fact that it's long wavelength as well makes it challenging to detect, but we can detect it. And we will see examples of that. So this is what my research was. It's using lasers to try to make these measurements. And so you start off with a YAG laser. This gives us that ultraviolet light, and it gives us it in short pulses. So you have short pulses of ultraviolet light. And so when the light is on, it goes through some filters. When that light is on here, it goes through some filters. It hits the sample. The sample gives off some light. We'll filter that light again, so we just get the bit that we're interested in, and we'll go to the detector. So what is happening here, we make sure that it's the ultraviolet light only, because this produces some other wavelengths as well. The ultraviolet light only is reaching our sample. The sample will then do its thing, and we've made sure that, first of all, there are no cells around and there are no other interfering effects. So the light that we're getting out of here should be from the singlet delta oxygen. This should be that phosphorescence from the singlet delta oxygen. And so we should be able to tell, if we do this experiment, how much we're making for every photon that we put in here. And these are the sorts of results we get. So we look at our detector and there's nothing, there's nothing, there's nothing. And then bang, the laser fires and we see that we've produced some singlet delta oxygen, and that gives off some light, and that slowly decays away. And it's the analysis of these two sets of signals through equations that look like this that enable us to say how much singlet delta oxygen we are making. Now, things have been made easy for people like me because there have been scientists that have worked out the quantum yield, so how many singlet delta oxygen molecules you get per 100 photons light going in, for some standard samples. So this here is a standard we use. And why we use a standard is so that we don't have to do the measurement really, really carefully. We can set up the geometry of our experiment however we like. And because we can compare the standard, we don't have to worry about the amount of photons we're collecting, because it's going to be the same in both cases if we don't move anything. The people that have done the standard have had to do it much more carefully than we did. So this is the standard, and you can see we're producing some singlet delta oxygen and it's giving off light, and as the light is given off, then the energetic oxygen has lost its energy. It's turned into the ground state oxygen, so it can't give off any more light, and slowly that we run out. And you can see the time scale here. This is 100 microseconds, a millionth of a second. This is a bit noisier data, but these are from our phthalocyanines, and you can see it's sort of the same. Now, what we need to do here is simply take those measurements, and you saw a set of measurements on the left, those different colors, they correspond to these black triangles, and we do that at different concentrations of the standard and different concentrations of our molecule. And then we take the gradients of these lines and we plot them here. These represent the gradients, and what we're comparing here is a zinc phthalocyanine. So zinc is in the center where that M was. We've got the phthalocyanine around the sides, and the R group is 15 carbon atoms long. So this is our shorthand. Rather than giving the full fancy IUPAC name, this is our shorthand. So we know the R group is 15 carbon atoms long. We've got a zinc in the middle and the phthalocyanine. That just tells us that we're dealing with the phthalocyanine. And ppn is our standard. And if we analyze those, we go through the maths over here, and what it boils down to is this. So the gradient of this graph compared to the gradient of this graph. Sorry, I got that the wrong way around. This is the reference, which is the ppn. This is our graph. That ratio of those two gradients is the ratio of the quantum yields. And if we know the quantum yield of our reference, which in this case is 0.95, we come out with a quantum yield of our molecule of about 0.74, I think it was, there or thereabouts, which is good. That's certainly something that we could, that would be useful for therapeutic purposes. So the other thing we can look at is the lifetime of the triplet state. So now this is that this is that blue arrow that I touched, you saw fading out on the Jablonski diagram that I showed earlier. Please excuse the tapping. If you can hear a tapping, please excuse that. It's just a nuthatch banging on the nest box outside my window. There it goes. So here we've got a slightly different experiment. What we're going to do is we take our laser and set it flashing again. Again, we're filtering out the light, so it's just the UV light that reaches our sample. And we've got a white light shining in here. And as the sample changes its energy levels, we should be able to see an absorption. If you look closely, you can see that that's changing to red. When we've got the light going in, we change the absorption of our sample. And we can see that here, if we take a look at the right wavelength. So if we take a look at a wavelength here, then we've got nothing, we've got no absorption, we've got no absorption, and then the laser fires and we start absorbing because we've made that triplet state, and that triplet state then slowly turns into the ground state. It slowly drains out of the triplet state, like letting the water run out of your bath. It drains out. Now here we've got the opposite effect. The second one, we're looking at this part of the spectrum, and that's because we've got no absorption, or we've got no change. We've got some absorption, but it's not changing. And then all of a sudden, we empty this out because we've taken molecules out of that lowest state and we push them somewhere else. And we see that filling up as the water dribbles out of the bath here, it fills up the state below. So we can see that everything's connected here. As we produce these high-lying states, the triplet state, as that drains away, that drains back into the ground state. And so you can see the energy flowing round our set of molecules. So this is our transient absorption spectrum. So this is where our triplet state is absorbing. You remember, we didn't have any absorption in this region for the phthalocyanine, but we've made it absorb because we've turned some of those ground state molecules into triplet state molecules. Finally, we'd like to look at how the energy from this, what's left in the molecule that's not fired out with fluorescence or phosphorescence or anything, how that ends up being dumped into its environment. And so we use a slightly different setup for this. We have our YAG laser again, we have our filters to make sure it's just the UV getting to the sample. But here we brought in another laser. So this is a laser that gives a wavelength 633 nanometers. You need a wavelength here that's not absorbed by your sample. Because what we're going to do here is use the energy that's put into the sample to change the density. Essentially, you're going to heat up the sample in a small region where the light has gone in and been absorbed, you're going to heat up that sample in a very small region, and you filter just the red light here. You put it through a small hole onto a detector. And so when you've made a region of lower density here, that will change the appearance of this laser beam. So what's going to happen here is that as we put energy in and it gets converted into heat in the sample, you make a little lens. It's what's called a thermal lens, because that is to do with the heat energy going in. You've made the sample a little less dense in that small region, and as a result, you've distorted this laser beam out here. And so instead of all of the laser beam getting through to the detector, only some of it does. There's another setup where you can have not all of the laser beam getting the detector, and then when you put the energy in, more of it gets the detector. So there are two slightly different ways of doing this. And this is an example of what happens. I hope you can see this. Now, the laser is flashing, and what you're seeing is here is a pinhole, and I hope you can see a red splash that occurs around the pinhole. That's when the laser hits our sample, and the red beam that's going through it gets distorted. And so you can imagine that at the moment, nearly all the laser, there's only a little tiny bit of red around here, nearly all the laser is getting through that hole to our detector. But when you see the splash of light, then some of the laser light's not getting to the detector. Here's another example on the other side. So this now is our beam. It's just going onto a black card, and you can see we're actually making a hole in the center of that. Let's run that again. See, right in the middle, there's a hole. I hope the system is fast enough for you to be able to see that. But
yeah,
what
I can see it.
You could see it. Well,
at
least one person can see it. That's good. That's good enough for me. Thanks, Leon. So what we see at our detector is this is no change, no change, no change. And then all of a sudden the laser goes off. You get energy dumped into your sample, and you make this lens which distorts that laser beam, and you get a change at your detector. And then it slowly, as the energy then diffuses into the sample around that, you get the laser coming back to your detector, so you get full beam as well. But the astonishing thing here is we've been dealing with timescales that we said were femtoseconds, 10 to the minus 15, picoseconds, 10 to the minus 12, nanoseconds at 10 to the minus 9, and even microseconds at 10 to the minus 16. But to get the energy out from this small region, we need half a second. So for that energy to diffuse out, to get back to an equilibrium where we're essentially the same temperature at all points of our solution, we need to give that a half a second to do its stuff. So that's the long time scale. That tells us that when we're putting this energy in, we need to give the molecules time to rearrange, to move around, to bump into one another, and to get that energy out. That's a much longer time scale process. If we look at short time scales, so if we look at this region here, this very sharp rise, and maybe up to this point, then we see something that's a little more interesting. And we can, so we've done this with PPN, we've done this with our various phthalocyanines on this side, and we can see that we get a very sharp rise to here, and then a much slower rise to there. And that tells us something about how the singlet state is putting energy into the environment, and then the triplet state is putting energy into the environment. And so we can get some information out about all the different phases of the energy going around this system. So we know as much as possible about what we call the photophysics. So that's the bit that I've done myself, and a postgraduate student helped me with that. What's happening in the future with these things? Well, the phthalocyanines need to be made more soluble. If they're going to be useful at all, they're going to need to be made more soluble. And one way of doing that is to use these things called cyclodextrins. Now, cyclodextrins are a molecule a bit like a polo mint. If you've ever seen a polo mint, you know, or donut, it's got a hole in the middle. And basically, the cyclodextrins are extremely soluble. And what you do is you stick a phthalocyanine in the middle in the hole, and that helps. There are other ideas of sticking phthalocyanines on nanoparticles and goodness knows what. You can look at the effect of the central atom. Now, it turns out if you put silicon in that central atom, you get fairly poor photophysics, the quantum yield for singlet delta oxygen. So the amount you produce, the amount of singlet delta oxygen you produce is relatively low compared to maybe the zinc phthalocyanine. But then if you know a collaborator, and in this case it was a collaborator in Italy that I was a collaborator of mine was working with, you do some tests with cells. You actually try this rather than just doing it in a test tube, you do it with cells. Then you find that the silicon phthalocyanine is much more effective than the zinc phthalocyanine, even though the photophysics says it should be the other way around. So obviously, in that case, there's not just the singlet delta oxygen, it's not just this energetic form of oxygen that's doing the job. You might consider other photosensitizers. So nanoparticles are very rich vein to look at. Silicon nanoparticles are thought to be benign, so they're not harmful in any way. Mesoporous silicon is another form of silicon made in a slightly different way. A mesoporous tells you about the size of the pores in it, and these are both tipped as potential photosensitizers that one could use instead of phthalocyanines. And then, of course, there's an extension to what's known as theranostics. Now, theranostics is an interesting concept where you're doing a therapy and some diagnostics at the same time. So you have a phthalocyanine, it can fluoresce, it can produce singlet delta oxygen, and it will do these if you shine different wavelengths of light on it. So you could imagine a situation where you shine one wavelength on to find out something about your patient or their condition. And if they need an intervention, then you shine your second wavelength on. So you've got a diagnostic tool and a therapeutic tool in one molecule or in one nanoparticle. So you manage to do both at the same time. And that is where I'm going to wrap things up. So thank you very much for coming along. Thank you for your attention, bearing with me all this time. And if there are any questions, I'm sure someone will let me know what they are.
Hello, no, thank you. That was brilliant. Very interesting. Some great stuff there to know about. So thank you. Yeah, there are some questions. So someone's put, where are we? Just give me 1 second to load them up. So there's one here. It says, how did you get into your career, and do you have any advice for how to get a role in the field one day, please?
Okay, so that's interesting. How did I get into my career? Blind luck, I'm afraid. It wasn't planned at all. When I was at school, I wanted to be a chef. I suppose chemistry and cooking, there are similarities. I just found that I was good at science. I found it came easy to me. And that led to university. That didn't come as easy, I have to say, but I did manage to get a place at university to study for a PhD. Having got the PhD, then I had no great career plan, but I knew there were these things called postdocs, which allowed me to work for a year in America and 2.5 years in Berlin, in Germany. The next step, certainly for an academic ladder, for me, was to get a fellowship. At that point, you'd normally either get a fellowship or a lectureship, and I got a fellowship which was 5 years long. I first started working in Bristol, and I realized that if I continued in Bristol, that there was unlikely to be a job. It wasn't impossible, but it was unlikely. So I started looking around, and the job opened up here. My first few years, my first sort of 8 to 10 years at UEA were fully into research. So I was doing this sort of thing. I was looking at molecules that affect the atmosphere and the chemistry of the atmosphere and how quickly clouds form at low levels in the atmosphere. And then I moved on to more science communication, which has been an absolute blast. I really enjoyed that. And so my research career sort of dissolved. I still do a bit, but I have a lab, but I don't know for how long I'll retain that lab, but I do have a lab, but I mainly do calculations these days. So advice on how to get a role in the field. Well, the field of research, you've got to be very interested in what you do. So if you're going to go the route of university, PhD, that way, you've just got to make sure when you do your PhD that you are interested. It's not enough to do a PhD because you want to do a PhD. Be really interested in what you're doing. After that, then it's, well, yeah, rather than do a PhD, you could be researching in a company and they might not require you to have a PhD. So you could go into that straight after a degree. The thing to consider there is that you would probably, for chemistry, you'd probably want an M-Chem. For physics, you'd be best to have an M-Phys. Now that M means that you've done 4 years of a degree rather than 3 years. Oh, pleasure. I say mine was blind luck because I just got into science and then I did the next thing and I did the next thing and I did the next thing and I found myself back home within striking distance of my family, it's just been really lucky for me. And I get now with the science communication, I get to travel around the world. So this time last year, I would have just got back from Malaysia and Indonesia doing kitchen chemistry for schools out there, which is a lot of fun.
Brilliant, thank you. Actually, I've got a question. You might be able to answer. So I work in automotive engineering, and we sometimes use welders.
Yep.
I just wondered, really, we obviously have to teach our students about the dangers of welding and getting arc eye, and we know that it's ultraviolet radiation that causes that. But why is it that literally it's just a flash? Is it, why is it like literally you only have to just glance at someone welding with your bare naked eye for a second or so, and you can get arc eye?
Well, that's to do with the intensity of the light. There's so much light coming out of it. It's like lasers. You have to be very, very careful around lasers. And again, you wouldn't look at a laser with a naked eye. In fact, you very rarely look at a laser with your eye directly anyway. But even with goggles on, they're just to protect from reflections and whatnot. No, arc eye is to do with the fact that it's so bright and it's on so very many wavelengths. It's similar to snow blindness, I believe, but there it's a lower level of intensity, but you're exposed to it for so very long. With welding, it's a matter of, it's such a high intensity, it gets concentrated on the retina because you've got a small spot. The eye tends to focus that to a small spot, and so what you've done is then damage those cells. I believe in some cases they will recover. The damage is not permanent, but that it's simply the intensity. You're using so much current for your welding that what you're doing is essentially what Filson did with a carbon arc lamp, although yours isn't a carbon arc, it's a metal arc, but it's the same principle. You're getting that metal hot enough to melt it through passing a current through it. If it's electric arc welding, you pass a current through it, and that produces light, and the light is so bright that it damages the eye.
Excellent, thank you. I always think of it as like sunburn for your eyeballs, but yeah,
that's a really good analogy, because sunburn in many ways it's just the same. You're damaging cells, and if you have too much damage in the same place, certainly in sunburn, those cells will never properly recover, and you're liable to have skin conditions as a result. And the same with your eyes, but you need to be much more careful with your eyes.
Yeah. I mean, most of the people that I know have had arc eye in the past said, I'll never want it again, and they're even more careful. So I think it's one of those things, if you get it once, you know about it, and then you don't want to do it again, because obviously long term it could damage your eyes. But I think just a one-off is not so bad. But no, thank you for that. I can't see any more questions on here.
No.
So thank you ever so much for joining
us.
Not
at all. I enjoyed that. Thank you.
Thank you. You take care. Thanks
and
everyone for watching.
Thanks. Bye.